So,
sorry,
yeah.
what is the brain-chip correction?
We talk about it as well. It will be the next step. Okay, so I told you before, we have image registration. Is basically putting two hands together in a linear case. But if we have a hand like this, we would need a nonlinear registration. We have to move the parts of the brain and put it into that hand. And that's exactly what we're doing if we are registering two brains usually, right? So in this case, we will have the MNI template, so a template in a normative brain, and we have your patient's image, okay, that we all processed. And we want to basically, with that approach, we want to create a stereotactic frame. So we want to have a coordinate system that is always the same. Right? In our template, we know exactly where each coordinate is. It's well documented. There's a lot of publications about it and all that. We want to move our patient native space now into this template space. And that's basically the basic idea used to be around for doing so since actually a long time ago, 1906, first time in cats and monkeys with the Horsley-Clark apparatus, and I think first in men was 1918, and I don't think they did it in a vivo man. I'm not an expert, so maybe Frank could help us with that, but it's not so important. The idea is that we have a specified space with a 0 point, and we would know that at each specific coordinate we have a specific structure. Right? So there were two really influential works, the Tyler and Turno 1988 and the Schattenbrand-Bahn 1977, which have basically started this and were also very influential. So the Schattenbrand-Bahn was really influential for neurosurgery, and the Tyler-Turno also for neurosurgery, but even more so for imaging. So for PET imaging, when people started using SPM and so on, the very first versions were actually in this Talirac space. And the idea was really similar. So most of these spaces use the anterior commissure as the 0 point. So 0, 0, 0 is usually at least around the AC. And the AC may be defined a bit differently and so on, so a lot of details. But then if you tell someone, I have a tumor at this coordinate, then they can look at it and they see, oh, it's the claustrum, right? So they know how this space is defined. And for functional neurosurgery, the Schattenbrand-Bahn was really, and it still is very influential. So here we can see the STN. So it's basically a histology image series acquired, and we see the GPI again, as you can now probably identify the lamina accessorius and lamina medullaris internus and then externus, and we have the striatum here, and we have here zona incerta, and this is the internal capsule. So if you have a certain coordinate system in the Schattenbrand-Bahn atlas, you can then know in a normal brain where is that, right? So these two systems, they had three important innovations. First is a coordinate system to identify a particular brain location relative to anatomic landmarks. Then they also introduced a transformation to match one brain to another, right? So they used your brain, your MRI, and took the AC and put it onto the AC of that, of these two atlases. And then also an atlas describing a standard brain, right? So you have a good definition of this standard brain. And the problem was each of them was based on a single brain, right? So they took one brain, sliced it up and looked at it, and then they put your brain on top of it and say your brain will be the same. And that is, of course, not so optimal. And then in the MNI in Montreal, they started the first MNI space in 1994, and they wanted to have a more representative template, like a more average brain, and really scanned a lot of brains and try to have an average anatomy. And as you can see, this was the first MNI space. It was really blurry, so you cannot see any details. So actually it's much worse than these, right, where you can see everything. But it was the idea to create a digitized normative brain. And it was really adopted to the functional neurosurgery, functional MRI literature. And then there were these methods to convert between Talairak to the MNI, and so they tried to create translations between the two spaces. And then this was the next one used in 1999, and it already looks a bit better, and you see now we already have a T2 and a proton density version, but it's still very blurry. And then they started the next iteration, which was the 6th generation nonlinear, which is still used widely by SPM and FSL. So now it's much clearer, now we have much more detail here. But unfortunately, this one was also only a T1. And then the really final one that we use in Lead-DBS is called the 2009 series. And as you can see here, we have a lot of detail with like all the structures, and this is really a normal brain that is averaged of a lot of brains together. And we have a T1, we have a T2, proton density, and so on. So this space is really well defined, not as well as the histological ones, but it's a three-dimensional deformable brain. And the idea now is to register a patient's brain into that space so we can know where exactly we are and where is the anatomy and so on. Okay. So again, most of the modern imaging pipelines use the one older one, and Lead-DBS uses the newest one. And I think there is a slight mismatch between the two. So sometimes if you have a result in SPM or FSL and you want to directly compare it with Lead-DBS and it's really about millimeters, there is some technicality to that. So you should be aware of it at least. Somehow, after all this development, the neurosurgical literature still stuck to this. So most papers that we read still have functional coordinates in this ACPC space, right? So they are defined something like 8 millimeters lateral to the AC and so on, or it was not 8, it was more 14 or so. But so it's relative to a reference point, and so I think there are more and more reports, and it's slowly coming that we should use more an MNI type of registrations, or nonlinear warp at least between two brains. And then this is just another thing that we also have like big brain data. That's what I showed you before. That we have whole brain histology now also defined in MNI space, where some people use took a lot of time to put resources into MNI space. So there are a lot of Atlaseas available for the MNI space and so on. And just for completeness reasons, we also have some other spaces like FS average used by FreeSurfer, and then the big brain, which is similar, but then also HCP templates and so on. They are all pretty similar, but this is something you should bear in mind. So we use by default the 2009B in MNI space in Lead-DBS, but we can, of course, as I showed you briefly before, also change to different spaces. If you're more interested about this, although it's pretty technical, I once wrote a blog post about this, and it's online. So there is a lot of detail about all these things, because as I showed you in the very first talk, millimeters really matter in DBS. So it can be important. I think if you're just beginning, it's not important, but it can be. Okay, you've seen this slide before. So what we've done now is to register everything to T1, to our anchor modality, right? We have, in our case, a CT, and we had a T2, we also had a PD, we had a F8 here and a T2 star. Everything is now in T1 space. And now we want to go to MNI space with that. And we use the post-operative data just to know where the electrodes are, but we use the pre-operative data to see where anatomy is. Right? So that's why the pre-operative is really important as well, not only the post-operative. Okay, so this step, I said it in the beginning, is called normalization by SPM, but it's still a co-registration somehow. It's just something they invented to make it clear that if we talk about normalization, we go from patient to template. And we adopted this terminology as well. Now I think we can skip that now. We had it before, sorry about that. So I told you about QSM and FGate here already, these specialized sequences. And yeah, so this is important now. So we have, I told you this is the SDN, or we discussed about it, it's probably part of the SDN and NIGRA in the MNI 2009B Atlas. So this is the MNI space, right, that we talked about. And now we have a patient here, it's also NIGRA rather, but some here probably up here might still be a bit SDN. But the idea now is to match these shades from here to there, and for example the red nucleus to this red nucleus and everything, and create a deformation that points each pixel here to each pixel there. Right? So that's the normalization routine. So maybe this is really anatomically wrong, but bear with me, I'm sorry about that. So here this is really NIGRA, but it's still the anterior part of this dark region. Goes to here and this goes to there. And now if we have the electrode here, that would also move somewhere here, right? So we use this normalization to have the electrode here. And now it's really crucial to have a, you see, to have a good definition, and you've seen part of these slides before as well, a good definition of the SDN here. Because if we don't have that, we cannot really use this. You see that? No? Okay. So let's assume our definition of the SDN is wrong, so it's up here. Then of course we'll get a very wrong picture between electrode and patient. So it also makes a lot of sense to know your atlas very well, right? So in Lead-DBS we have a lot of atlases, but that doesn't mean all of them are really good. So it's rather a library of the open science literature, and to really think about these things. So it's not foolproof, so it's rather tries to be exhaustive. So they need to fit, and this is, I've shown you before, it's our solution. So it's this distal atlas where we really try to make the SDN and these main structures of the MNI space fit the MNI space exactly. And then we added histology, so there's a lot of data really available, and really try to make a good job in registering also the histology and everything very nicely to this 2009 MNI space. So if there's not a good reason to not use this one, I would maybe not, or you know. So I would think as a starting package, this is really a good atlas for Lead-DBS. And as I showed you before, we also made this differentiation between the parts. Maybe some more information is that we have parts of the atlas which are here in blue, which are basically made based on structural connectivity. So we divided the SDN and also the GPI based on structural connectivity. But we also made some of the main structures like SDN, red nucleus, GPE, and GPI just based on the templates of the multiple modal 2009 templates, and then we filled up the gaps with histology. So it's basically an atlas that is defined by 3 different sources of information, and each for what they're best for. Okay, but now, yeah, let's do that later. Just hands-on. But we will probably now move to normalization. Okay. So, nonlinear co-registration, also called normalization. We've talked about it. The idea is to match 2 images, right? So this is a bit off topic here, but you may still know Obama. This is our head of country, Angela Merkel. And the idea now is if you had only their eyes and you want to match them, then it's simpler in a linear fashion, right? So you could blow them up and make them really big, and then if you put them over each other, it's not even so bad. That's what we try with the old school methods, with the stereotactic methods, where we fuse the AC, and since our targets are not so far away from the AC, we think it may work, right? But we still get quite some errors in this registration. And the other way of doing it is nonlinear, so having really taking each point and putting it on a different path, right? And that would be like this, right? So you get a better registration between the images, right? So I think everybody should now understand what the difference is between linear and nonlinear registration. But in this case, we try to do nonlinear. So here you can see the origin. So these lines were originally horizontal, and they were now deformed to match the template, right? So the patient was slightly squished around and warped and deformed to match the template. And inside Lead-DBS we have quite many methods to choose from. And in the beginning this may be a bit overwhelming or so, but what we have identified, and I'll show you some results later, is actually that the SPM segmentation is really great, and also the ANS SYN multimodal registration is really good. And there's one really important study in the literature that tried to compare the registrations, so nonlinear registrations for the cortex, so not for the STN or so, but for the cortex. And it's been cited really over 1,000 times by Arno Klein, and what they concluded was that these two methods, so the SPM data and ANS methods, were the best in that study. And when we read that, we thought, okay, we'll take Dartel and ANS, and that's great, so we entered all to Lead-DBS. But Brian Adams, the author of ANS, also said ANS changed quite substantially since the Klein paper in nearly every way. So this was already a bit outdated. And then the next successor for Dartel was already out, which was Shoot by John Ashburner. So this study is already a bit outdated. Here, this is a Shoot example, so we can see the cortex really lines up pretty well with Shoot, and we were pretty happy when we added that as well. But the problem is that this was all about the cortex, and we were interested about the subcortical structures, and the SPM methods all based on this SPM segment, which as you may see, so this is the gray matter information in the MNI space of segment, and it totally lacks the subcortex. So the STN is not recognized as gray matter here. And what some people did, so nothing to see here, but some people then, so Bogdan Regansky's lab, they created new TPMs, new enhanced tissue prior maps that would also have a good definition of the subcortex. And we tried these maps, and we then also built our own that are a bit similar for Lead-DBS, that are basically have even a better fit to the STN. And so we now have the TPMs that we use in Lead-DBS, they have really good definition of the STN, and they also have a really great exact ICD-M 2009B fit. But it's the same idea as Torgansky's lab did. And this is a result, so it's also an old image, and you see today with our patient it may even look a bit better, but we have a pretty nice overlap between the STN of the Atlas and red nucleus and the data below it. And we thought in the beginning, of course, the newer methods are great, so Dartel and Shoot and SPM segment was older and so on. But at some point, a lot of people always ask us which is the best method, and also they ask us what is the average error of Lead-DBS. And it's really hard to say because we don't have any ground truth. But fortunately, Siobhan Ebert and Todd Harrington in Boston, they wanted to really find out, and what they did is, so we have the STN definition in MNI space, and what they did is they segmented over 100 STNs, and 2 people segmented them, so they had 2 segmentations, and they did the same also for the GPI, And so these are the manual segmentations, these are the automatic ones. So they use the MNI atlas to transfer it back to the patient, then compare it with the manual segmentation. Right? So they basically wanted to see whether Lead-DBS can segment the SDN as well as manual. And then they did that on 2 cohorts, one on healthy young subjects and one on like more older patients that were matched to Parkinsonian age, and also on a 1.5 Tesla scanner. So this is basically poor quality clinical type, and this is a best quality or good quality young people. And this is wrong. And what they concluded in was that ants with the subcortical refine that we introduced and SPMU segment were actually the winners. So the newer SPM methods actually were worse than the old one. And the ants also worked with a more rigid paradigm. So what we conclude from this is that if we use these very new methods that are optimized for the cortex, they may do too much to the subcortex and even move the nucleus a bit too much around. And the older methods that are more conservative seem to have better results.
So whatever is worked, we did it in 40 patients or so, and we found the same.
You found the same?
Yeah.
Okay. Also the older methods. Yeah. Okay. Interesting. That's great. So they actually, if you have the inter-rater surface distance, comparing it with ants and SPM, you see no significant difference. So you see a slight difference between the dice coefficient, but it's really not big difference. So somehow they conclude it's nearly as good as manual expert segmentations. Okay, so questions up to here. It was pretty much, I think, already, but basically to sum it up, what we found, or what they found in their study, is that older methods are pretty good, and what I didn't say, what they also found is that if you have multiple preoperative images, it would also be better. And nonlinear normalizations are a method to warp a patient's brain into MRI space or back. Right? So that's what I basically said. Now, what we also did a lot is to use multimodal normalizations. And that means that you have your patient data, you have the T2, and you have the MNI space, and you also have a T2 template. But you could also then add a T1 and a T1 template, and the proton density and the proton density in MNI space. And then you feed all that into the same algorithm, right? So you basically tell it in the beginning, you give it all the data and you give it all the templates, and it tries to find one normalization scheme that best fits them all. Right? So you find one warp that basically tries to match all these 3 arrows. Right? And in the end you get one arrow that will point from each pixel in the patient to the MRI space. And of course the algorithm gets a lot of more information if you have so much data, and also, for example, here you can see the SDN well, here you can see the GPI well, here as well. So it really helps to create one good warp. And then we thought, what about white?
Which of the routines does that?
So in Lead-DBS, all of them, except FSL. So all of our methods are multimodal by default. Yeah. So this is the ants way of doing it, but SPM does it a bit differently, but also uses all the information. That's why we put so many preoperative images in there.
And what about face?
Face?
Face.
You mean face with pH?
Like SDI or
Yes, so I'll get to that. So first, before that, we thought about what about white matter, right? What about, for example, these areas where we have no information at all in the T1? Then we thought, okay, we can also add the FA information. If we have DTI scan, we can also use the DTI and warp it to a DTI template. And so that led to then the FA to FA as well. Now you have 4 that you can add. But then we also thought, like, what about these really cool new sequences that QSM or Lead-DBS or whatever? And what we do in Lead-DBS is we pair it up with a synthetic template that we call the PCA template. And that is basically an aggregation of these three put together as one, as a like principal component analysis fashion. I can show you that template. So it looks pretty nice, I think. And so that's this aggregated PCA template, and it has a good definition of both the TPI and also the STN down here. So it's basically best of all worlds. And since we don't have good templates for QSM or for whatever other sequence F8 here, each sequence that it doesn't recognize, Lead-DBS will now pair to this PCA template by default. You can change all that, of course, but that's the default pathway. And running such a multispectral normalization can take quite some memory of your computer, but it leads to pretty nice results. So we did do that. So we had a T1, T2 proton density, T2 star, and F8 here in our sample patient. We didn't use ants, but we used segment, and segment does it a bit differently. It aggregates these first and then walks into MNI, but we did that, and we can look at the results pretty soon. Right? So this is the idea. So main take-home message here is really that your preoperative data matters a lot, right? For precision, the better and the more sequences you have preoperatively, but all of them need to be good resolution as well, the better. So I know this is always a problem to scan patients long time, and especially with the numbers in China. I've heard you may sometimes make 3 operations in the same day at Tiantan, right? I've been there. So this is tough, but it's really worth it. If you want to know this really millimeters information, I think the preoperative data is key. And optionally on a 3 Tesla scanner and so on. So, okay, but questions for?
Not the preoperative data. When you import the diagrams to the NIFTY and you do that step, there is like I don't know which measure you use to say if the data is suitable or not for the analysis.
So
what would you recommend?
Yeah, so I would think anything above 3 millimeter resolution I would not use at all, and even 3 millimeter is not good. What would you think? Yes. The better, of course.
Better, but
yeah, I mean,
yes.
often people have a 1 millimeter MV range. That's a good start, definitely.
It's often optimized to have something with a higher intent resolution.
Yeah, often it's like
a swine on with a higher intent resolution.
So I don't have any
The FA
data.
map is the one that tends to be the lowest.
Sorry?
The FA map is the one that tends to be the biggest.
Yeah,
Oh.
yeah, and then I would probably rather not use it. If it's more doesn't always help, and it's also good to run tests actually on your settings. So what we did is we have these 5 sequences now, and we optimized them a bit, but we also ran the same subject just with T1, just with T2, and just with a few different combinations, and then really looked at the results. So this is not empirical, but it's not really good to measure, but you sometimes see whether the additional sequence really helps or not. So there are not good data on this. What I know from the study that I showed you is that adding more with good resolution definitely helped. So T2 plus T1 did improve results definitely over just T1, but also over just T2. So I'm pretty sure it helps.
Did you ever run some sort of cross-validation about that when you have, let's say, T1, T2, proton density, and FA, and then just leave one out and test how the accuracy is affected when you leave one out? Particularly with FA, I would be interested, because with FA I would be a bit scared that even FA might have made it worse.
Yeah.
It might have geometric distortion and low resolution, so it could in principle happen that adding that modality makes it worse than just using the other three.
I agree. I would also think that FA is probably then really important if you are really interested in fibers in the end, right, in a study, and then you need a good FA with distortion correction and so on. But I agree. So adding FA is probably usually not a good idea. Just
More advanced.
yeah, I agree. Yeah. Okay. So, but what we can do now is we have all normalized the patient, and we can really look at the results of what I just showed you really is true. Whether you believe me that it will have a good result. And what I already did is to run the check results again. And if you had approved all of the images before, then you should directly see this. If not, you have to approve the co-registrations before, but then you should see the GL anat up here. That's important. That's the normalized T1 and then the T1 template. So it's the same view as in co-registrations, but it shows us a bit different things. So here the red wires are actually the MNI states, right? Now this is really the normal grain, and the GL anat is the normalized T1. So maybe again raise your hands, everybody who can see this on their screens now. Really good. Anyone who wants to but didn't make it? But you right.
I have a question, because on our paper when we were running it, we couldn't finish the step doing the normalization and the brain shift at the same point. So we ran the normalization, and if we skip the brain shift, it was okay. But when we put both together, we had a that we were using DBI. It might affect the brain shift correction or.
So, but did the normalization fail or?
No, the normalization was okay. But we were running, we did step by step. So we were doing, checking results, and when we
I've never heard it, so it should work. Maybe update at least, and then try again. Might have been fixed, but we haven't had this problem. So I can't really say anything. I think I ran it both. Okay, so this step is really crucial, right? Because here what we want to do is we fuse the patient with an atlas. And in the end we look at the atlas and the electrode. So if this fusing process doesn't work well, then the whole information you gather is not valid, not helpful. So you should really, really understand this step. It's more important than most of the other steps, I think. Right? So, and that's why we try to make good check results or good ways to check this. And one is just to look at this image, but that's really crude. And then the other one is, as you've seen before, the detail viewer, right? So that should hopefully work for all of us now. And what that shows us is the MNI brain. This is the patient brain normalized to MNI. And if we click, then we should see the MNI template below it, right? And it's especially important down here where we have the, where we have the basal ganglia. There, the registration needs to be really good, right? And the other thing that you can do is press X again. Again, we have the shortcuts up here, and maybe Z for zoom. Then you zoom it, and now you see the wires, which are these white lines. These are from the template, and we see our data. So the normalized T1 in the back of that. Right. Another option that you can do is to show other preoperative acquisitions down here. Right. So if I press 2 now, the letter 2, in the background, you can see something's processing now. In the background, the T2 image will also be warped into MNI space. And once it's done, it will show us the T2 image and the T2 template. And of course, that's also really important because it's about the STN in this patient, right? So we want to also look at the T2. Now it's done, and now we see the T2 image. And in the patient folder, now, oops. The patient folder, if I sort by date, we have a new file now. That's this GL and T2, which is the normalized T2. GL, it's historical reasons, but it's called the T2, normalized T2. And now we can scroll through, and this is actually the region where you can see the STN, right? You see the white lines here. This is the STN, and it should also match the STN of the patient. So this is really crucial. And you may now say, looks okay, but I can't see it good enough. That's true. So we'll even have more ways of checking quality, right? But this is one idea where you can see the STN of the template and then also the shade of the patient's data. You can press 3, then it will create the next preoperative data, and also you can look at that as well, right? So if you, for example, in this case, we have an F-gate here image, so we can also look at the GPI normalization, or there's a T2 star, so we can really look at specific data sets. This is now not a good example. It's probably PD. Yeah. Okay. And yeah, so it's GL and PD set it up here, but it's not windowed. Okay, so it's really important. Everybody got this, but we're not done. There are more ideas how to check the accuracy. So this is the F-gate here now, and we can look at maybe the striatum, which we can see pretty well here if it's well aligned to the striatal lines. And if we click, it shows us this PCA template in comparison. Okay, that's one thing. The other thing is to use this check structures button. If you click on that, it will show you how many, these were our preoperative images, right? And we can now say we want to see the T2 image together with maybe the distal atlas STN, right? So we go, show me from the T2, show me from this atlas the STN in comparison. If we click that, then we get an image of just just the normalized T2 and just the STN, right? And it's just one picture, but it's a quick way of comparing how well was the STN of the patient normalized to the distal atlas. And on my monitor, we can see it much better. That in this case, it's really worked really well, but probably you can see it on your monitor as well. So again, check structures T2, then distal atlas, and STN. Maybe try that. You have to click once and then wait. Okay, it's still here. Here you can see, right? It's a nice match between the dark and did everybody manage to do that? No, this view, no. It's more a quick view.
So we can project the display and try to slice.
Yeah. Definitely, yeah. Yeah.
Not something we have been using, but I'm just thinking about it now. Can you break the normalization just like we do for the paper?
Yes.
Can you? Is that easy to do?
Yeah. So quick answer.
If you think about surgical planning, you will have to have it in the clear space.
So it's all you need to do is basically visualize it in native space, and then it will warp the atlas back to the patient space. The other option is in here where you say map file from template to anchor space, and then you select any nifty file in MNI space, and it warps it back to the patient. Okay, but let's say we're still not convinced. We still want to really check, it's about an important patient, and every patient is important, sorry, but we want to, really be sure. We can also look at the files themselves, right? So we can click on the patient directory button up here, and it will open just the folder, and we can go back to Slicer. And for example, we can say we want to use the GL, so the T2, and we drag that into Slicer, right? And then we go to this folder here, so Lead-DBS, templates, space, and then this weird MNI space that we use. This is an important folder, maybe you can bookmark it or so. In there we have all the templates of the patient, of the MNI space, but also the Atlaseas and everything. And I think you should also see an image that's called stn.nifty. Does everybody see that, or is it just in my, okay. Yeah. Then we can also drag that into Slicer. Right? So now we have just an image of the distal defined STN and the normalized T2. And so in Slicer you can overlay two images and fade between them, right? So we can now fade between them, and we can even make it a bit nicer if we click up on this volume thing here and then select the STN and say maybe we want to make it red and like this, and threshold it a bit, and then and we only see the STN. So, right, so what we've done is we have loaded two files. One is the normalized T2, one is the STN from the Lead-DBS folder, and that was again here. So it's in Lead-DBS templates space MNI template, and then the stn.nifty.tc. And we have loaded the T2 of the patient, and then in Slicer you can select two images. So we have selected the T2 here and the STN here. Then we went onto this button to volumes. We've selected the STN here, and we have thresholded it so we can only see the STN. And now we can make it semi-transparent and really look at the correspondence, right? So we can really look at whether this atlas fits the T2 of our patient. And I would say it matches it pretty well in this example. Did everybody get that, or was it too fast?
Can you show me where the file is?
The T2 you mean?
The STN used in.
Yeah, so it's in Lead-DBS, then templates, then space, and then this folder, the MNI STN. We'll create STN It's called Atlasea. Inside the patient called Atlasea and distal. Okay, so these are options of how to check the registration, and I would say it always depends on how, like, what your question is, whether you need to do all of these steps, right? So if your question is you have 1,000 patients and you just want to know roughly where the electrodes are, then maybe it's not that important. But if you have a single patient that needs lead revision, you shouldn't use Lead-DBS anyways. But if you do, you know, then it's of course much more important that the information is right. Right. So it's really important that at this point to understand that with this tool you can also get a lot of wrong information, and you really need to understand what is happening, because little millimeters make a big difference. And these are now 3 ways of what we can do to check normalization. Right? We had the first view, very overview, then we had the detail viewer, we looked at the T2, then we checked the structures with this button, and then we also opened the files in Slicer and could really understand more specifically. Any questions up to here? Reverse?
Yeah, reverse. So I can get the SDN something.
Okay, why don't we do that? So let's say we are happy for now, and then we reverse it. So if we're happy, we can again click on approve the next, and then it will probably now show me the range of correction, but we will do that later. And what we do to, you mean you want to walk the STN back to the patient, right? Yeah, okay, let's do that. So what we do to do that is to press render 3D, and we still select the distal atlas, but we now select the native patient space here, right? That means we will now work in native space, and we press run, and it will now, in the background, generate copies of the STN in the patient space. And so, as you can see in the background, it's running and it's warping the atlas files back to the patient. And in the patient folder, we can now see a new folder that's called Atlases. And in there, we have this atlas. And as you can see, it already warped files there, and it will now, finish these files. And once it's done, it will show us the files. And we can. That's the 4th way of checking the registration. So we have now the normalized results of the Atlasea, and I think usually it looks smoother. I have some weird settings in my developer version, but on your side, if it's already done, it should look a bit smoother. But what we can also do now here is to, so there's this small window, this one, where you can also select the preoperative data that you want to use, right? So if we switch that to the T2, then you see the T2 image now together with the the patient-specific or like walk to patient space STN. And we can also use this to check for accuracy, of course, right? Because now the T2 should show the STN at the same spot where it hits it. And maybe we can also, in this window, we can enhance the contrast like this. Something is weird here. Like that. Maybe now we have more contrast. And we check, so this is the STN shade, right? And if we put it on, then we see it projects nicely. So looks bigger here, but that's just because 3-dimensional, right? So if you go up a bit, we see that it hits exactly, or more or less exactly, the black or the hypo-intense zone. Right? So this is another way to check registration, of course. It's just the other way around. Now we are in native patient space, And what we can do now as well is to do the same process we did before in Slicer. So I close everything in Slicer, but now I take the anode files, so the native space files, like this, and add them into Slicer. And I can also add these newly created files, like the STN of the left hemisphere in this case. And then we can also look at the, the T2 with the STN. So should fit nicely. Let's see. You can see the STN better. It's really hard to see here, but maybe on this T2 star. So we can see it pretty well on the right hemisphere here. So let's take the right STN and compare those. T2 and this STN, and you can compare the definition of the T2 of the native space and the STN, and it should look really similar to before, right? Because we wanted to say so this is the Atlas STN now. And if we go back to just a T2, I think the agreement is pretty good, right? And it might be so good because we had a lot of preoperative images, and we gave the algorithm good clinical, like 3 Tesla data that where we can really find the STN. Even though I agree this data doesn't really look really good. Okay, so we're a little bit over time already, but I think this was important. So this is really one of the most important steps, normalization. Please approach us if you haven't understood it or if you have problems or so. And I would still now hand over to Xinyi to give you a talk about the ES here in Shanghai. And then after that, we have Friederike talk about electrode reconstructions.